So we stopped here with this adaptive procedure. And I would just to mention the surprising results by Blanchard and Roquin very recently, that if one instead restricts the story estimator to very small ones, that is, we measure how many big ones we have, but not over the upper half, but going all the way, say, to 0.05, to the same level as Q, then this thing shrinks back. The variance shrinks back, and then we're doing much better and almost controlling. And these two have some very nice additional results about that. Okay. The third one is, I would like to explain the third, and it's especially because I want to use it later on, but it's also one of the things that, that we have a proof about. And it just, I would like to mention, so it's the third adaptive method. And it's, in a sense, a combination of Holm and the BH. In what sense? If you remember what I showed with the Holm, you start with P1, and at each step you compare Pi with alpha over m plus 1 minus I. I mean, this is the size of the family that you have at stage I. At stage 1 you have m, at stage 2 you have m minus 1, and so on and so forth. And you stop whenever with the first non-rejection. Now, the multi-stage FDR controlling procedure, you also start with P1 with the smallest p-value and work your way up. At each time you compare Pi to Q over I, now remember, in the adaptive case, we want here to have m naught, we put it m plus 1 minus I times 1 minus Q. So not minus I, because among the I you might have Q, which are false discoveries. So you're not sure, you're sure only about 1 minus Q. And you work your way up to higher p-value, reducing the size of the family each time you go up by 1 minus Q. And you stop with the first non-rejection. And what you have really is, forget the formula, and what you get really is that you have both FDR controlling properties of this procedure and asymptotic optimality. Asymptotic optimality in the size of the problem under independence. As the size of the problem increases, what you get is this kind of procedure. This is the way the constants look. So you see, it's over here, it's linear with the same slope as the linear step up, the BH procedure, and then you allow yourself more and more as you go up until at the end you compare with I over m plus Q. I mean, you really, you compare it m over m plus Q, very close to 1. If you plug in here m, you will get here and here, you'll get m over m plus Q. So at the end, if you got there, everything is fine. You can allow yourself a lot of leeway. Okay. I will use this in the continuation of the talk. Now I want to just briefly present two areas which I will not talk about. One is the Bayesian and Empirical Bayes approaches. It started with Tusher, Efron, Chan et al. In the context of gene expression analysis. If you threshold significance, and at that time it was 4,000 genes. If you threshold the significance at some alpha, at some A, then you can define the positive FDR, which is the expected value of V of A divided by R of A. So this is the proportion, given that you have rejected something. So this is the conditional, the positive part that appears. And so it is almost, it's FDR if you threshold at A, divided by the probability that you will reject something. And in large problems, this is approximately the same as FDR, but this cannot be always controlled. Efron continued with this line of work, and with papers starting from the 0.01 paper with a few more, and then his recent large-scale inference book, very nice, very illustrative, and the book 1910, and he talks about this approach at length. He defines FDR. Okay, you see the capital in the F. He apologizes and says it's such a good name that he can't avoid it. So he says FDR, and this is the expected value divided by the expected value. Okay, instead of the expected value of the proportion, expected value divided by the. And this is, in large problems, it's the same as FDR and the same as the positive FDR. But then you can take its derivative and you get the local FDR, which is essentially getting close to the Bayes factor and so on. This is P naught, which is the proportion of null hypothesis, times the density under the null divided by the density of the distribution that you have. It's P naught F naught X plus P1 F1 of X, so you have really the Bayes factor. And the empirical Bayes in it is estimating P naught, that is the adaptive methods we use. These are the empirical part here. And in later work also even estimated F naught to make it empirical. And so this is this by itself is a whole talk that I cannot get into it, and worth listening from Efron himself. The other thing I will not get into is weighted FDR. So far, we have looked at all hypotheses equally. Everything was on equal footing in a way. Weighted procedure make distinction. Each hypothesis HI receives a weight WI, and now we can do two things. I mean, with the sum of the weights being equal to the sum of the hypothesis. We can try to capture by the weights the importance of each hypothesis separately by defining a weighted FDR. Sum of WI RI, that is, if I reject, other way around, sorry, sum of WI VI divided by the sum of WI RI. And so it really allows us to give monetary value to each rejection. And this will be the wasted cost in our discoveries. The other one is by Genovese and Wasserman. The advantage, you give advantage to each hypothesis by taking its p-value and dividing it. So this one can be bigger than 1. So you just lower the p-value. I mean, you really give it advantage. Of course, it has to come on the expense of other ones that will have less than 1 weight, and so they will get disadvantage in being discovered. For both of them, and actually even you can use this one U, and FDR is defined just as before, and both are, in my opinion, underutilized in practice, and they are important, but I will not get to them. Maybe that's the reason they're underutilized. Okay. So that was the planned end of the first part, and let's go to the second part. By the way, FDR wasn't easy to be accepted, and in 1998, one of the currently workers in the field, Helmut Finner, started his talk by showing tombstone and saying, "Here lies the FDR." He found some terrible fault in it. It doesn't control the family-wise error rate. I mean, we give up something in order to gain this. Okay. So what I want to talk now about the false coverage rate, and you will see that now some of the ideas just appear again, some are new. What appears again is the fact that the marginal standard 95% confidence intervals, they offer the probability that the marginal interval covers its parameter with probability 9.5. Or equivalently, the probability that it fails to cover its parameter is 0.05. This is for a single confidence interval made on a single parameter. Now, with many such intervals, the probability that some intervals will fail to cover increase to above 0.05. Using simultaneous confidence intervals simply assures that for all of them together, there will be less than 0.05. So far, there is nothing new. But the fact is that people treat the problem of multiplicity as less severe with confidence interval. Okay, you can find many reasons for that. In epidemiology, they say hypothesis testing is simply no good. You should do confidence interval. Now, confidence interval you shouldn't adjust for multiplicity. It's only post hoc analysis that you have to adjust for. So you're doing better science. You shouldn't be punished for doing better science by confidence interval rather than confidence interval. More than that, why do we bother about multiplicity? What is the property of a confidence interval? The confidence is that on the average, it will fail in less than 0.05. But the expected proportion of intervals that failing to cover is also less or equal to 0.05. If you're doing 100 confidence interval, on the average, it will also be less than 0.05. So why bother at all? Okay? So let me explain you what bothers me, at least, in that, and why I care about it. Okay, so we have 20 parameters, and I want to estimate them with 90% confidence interval. And these are the true values of the parameter, and you see that no one actually, well, you may argue this one, but nothing is zero. So the null hypothesis is never true. Fine, they are not true. Now I have estimators. For each one of these parameters, I have an estimator. Of course, they vary widely, but that's fine. The confidence interval, I put one confidence interval, 90% confidence interval about them. And we see that some intervals cover their parameters, and some do not cover their parameter. This one fails to cover its parameter. But if I'm looking on the average, only 3 out of the 20 do not cover their parameter. I made a 90% confidence interval, so this should come at no surprise. I have one coverage. But let's look now at all those intervals that do not cover 0. Okay, now this one doesn't cover, this one cover, this one doesn't, and this one. Now I have 4 that don't cover 0. And let me select those that do not cover 0. Okay? Now once I select this, 3 out of the 4 do not cover when selected. Okay? While there is no hypothesis testing, the null hypothesis is never true, just a matter of coverage. When I select, coverage deteriorates, may deteriorate. And the more extensive the selection, the more likely it is to not being able to cover, even on the average, the properties of that. Now, this is partly the reason why in many studies, when you look at the bigger ones, then in later studies, they shrink back. I mean, in later studies, the same phenomena doesn't appear as surprising as it was before. It was selected in the beginning. Now, it's interesting that nothing is safe from this effect of selection. Even Bayesian intervals that seem not to be related to that may have the same phenomena. And there's a paper by Wang and Lagakos, and more recently by Cutielli, explaining this point and making the distinction when it does and when it does not. So let us define a false coverage statement rate, which means that if I have data T, and I'm going to select based on the data a set of parameters, and to state confidence interval only for the selected set. Let me define the false coverage statement rate, FCR, of a selective confidence interval procedure as the expected number of the number of intervals that I'm making that fail to cover their respective parameter. The parameter is not in the confidence interval, divided by the number selected. So I'm looking at the proportion of intervals that I make that fails to, very natural thing. Again, S may be 0, I may select nothing, in which case the ratio is 0, and FCR is the expected portion of coverage statement made that failed to cover the respective parameters. And similarly, I have an FCR-adjusted selective confidence interval procedure, which surprisingly takes into consideration only the numbers selected. So the FDR selective confidence interval procedure is apply the selection criteria, and for each I in the selected, construct a marginal confidence interval, but at a more conservative level. What is the conservative level? The number selected divided by the number from which I selected, the potential number that could have been selected. So I inflate the confidence interval in this direction. And the theorem states that for any simple selection procedure S, if each marginal confidence interval is monotone in alpha, that is, if I take and 0.05, 95 level margin confidence, it will be shorter than 99. It will be shorter than very natural condition. And if the component of the T of the test estimators are independent or positive regression dependent, then the above FCR adjusted CI enjoy that FCR is less or equal to Q. And I believe that many who look at that can see the connection between the FDR and the FCR. Because essentially what you have is that if you test whether mu I equal to 0 and you select the controlling the FDR with BH, then exactly what you have is that you select I if and only if the FCR adjusted confidence interval doesn't cover 0. Because here you have R over M, the number that rejected over M. Okay, as for the original BH, if the selection is I, that is if you select S is small and wider intervals are needed. If S is 1, these are the Bonferroni confidence interval because they are at level 1 over M. And if all are selected, nothing is needed because the number selected over M is 1, and if there is no selection, on the average, it's fine. I mean, whatever you do with each single one. So the FCR adjustment is adaptive. Simple, that is stated up in the theorem, need not be that simple. It is Bonferroni testing, unadjusted testing, using BH, using the largest K, and so on and so forth. They are all simple in this respect. Adaptive FDR testing is not simple, but the only difference between simple and not so simple is the definition of number. You count in a more complex way, which I'll not go into it. You count how many effective number that you have, and this effective number might be different, and then you plug the effective number there instead of this, actually the number. But in many situations, it's there. Now let me emphasize again. If you select not based on the data that you're watching, you don't have to worry. If you predefine what you would create confidence interval, there's no problem. The problem here is, again, that you do the analysis and then select what is interesting and what is not. And so this is the important point. Let me give you an example of a massive selection, and this time it's done not by the abstract, but by the table. This is a very important study of application of genome-wide association signals in UK samples that do analysis for type 2 diabetics. The connection between type 2 diabetes and a scan of the genome. This is the table in the paper. You can't read it, of course. You know, I mean, I don't expect you to read it. But what you have here is a list of 10 SNPs, just 10 SNPs. And you have here different studies in which it was tested and so on. Then looking at all combined 14,000 cases, 70,000 control. And what you have here is the odds ratio. I mean, for those who are not familiar, it's the increase in risk, approximately the increase in risk. If you have this SNP in the one form or another, and so it's 117, 112, and so on. This is the estimator, combined studies. And this is the confidence interval. And since you can't see, here it is again. So you have the list of SNPs. You have the odds ratio, and then you have the regular 95% confidence interval. Now, this is typical in the sense that these were tested and adjusted. In fact, they were adjusted using some version of Bonferroni. And so only 10 were selected out of about 400,000. And so the p-value that exists there are extremely high. But when it comes to the confidence interval, this is the regular marginal confidence interval. So you see here that, say you have here from 7% to 17%, from 14 to 25, 8 to 20. I mean, they're very strong results relative in this kind of studies. Okay? Now, if you do look at it with FCR adjusted CIs, and the factor there, instead of being 0.05, it's 0.05 times 10 over 400,000, then these are the FCR adjusted confidence interval. And you see that it goes from 1 to 130. It goes from 1.1, so maybe there's an additional only 1% here. That's also reasonable. And from 3 to 36. And suddenly the uncertainty that is merely due to the selection is much larger. You will not be surprised to find only 1% increase in your next study. Okay, and this is unfortunate, but this is the way it is done. How well do we do with this kind of procedure that I showed you? Does it have any sense of optimality or something like that? Well, sometimes it is the best that can be done under some additional condition. If for all I you have some ui, and ui either is very big or is at 0, then what you have for the FCR is that it goes from 0.05 all the way to 0.05 and no more than 0.025. So this is at most what you can gain in some situation. Okay? But the story is more complicated than that. And for that, I have to do a simulation and show you the result. So here there are 10,000 estimators of 10,000 estimators, and here you have the observed y, and this is the effect size. And what you have is a threshold. It was done using a threshold of the BH. So only these were selected. And the selection was at 3.11. So these are the values that were selected. They are brought in this form so that this is the unadjusted confidence interval, and this is the FCR adjusted confidence interval. This will be in one place, and the observation move around. So the confidence interval will cover if the point falls inside. It will not cover if it falls outside. Okay? And what we see clearly is that the unadjusted are really bad. This is the red ones are the unadjusted, and many observations fall outside of it. And in fact, if we look at the green one, which is the FCR adjusted, well, we're doing quite well here. I mean, there's nothing, there are a few here that come out of here. So on the average over the selected, we're doing very nice, right, in this situation. However, if you look here, they're much too wide. I mean, look, we are not even the regular would have been done well in this direction. Now, why is that? That's because we have chosen the biggest. By choosing the biggest, we have created bias in the direction, in this direction. So we have to increase in this way. But it seems that if you choose this method, you don't need to go that far in the other direction. That is, the method of selection can be utilized in order to maybe get a better selective inference confidence interval, and possibly also tests. So the next couple of minutes, what I want to show is exactly what happens on this kind of thing. And the lesson I'm trying to drive in is that we can do better than merely protect against any selection, which is what the FDR does and what the BH procedure does, and this kind of. So the point is the following. In particular, let me take the selection of a parameter if its estimator is big enough. So I have y's, but I'm going to use y only if it is bigger enough. So this is, C can be the significance level, it can be as before. And so C can be either fixed or simple data dependent. So I have this one, and this will be my criteria. And so if I look at the conditional distribution, they're very different from the original distribution. This is the original Gaussian distribution with mu here. If I take the conditional one out here, then it goes up here, and here, of course, it is 0. If mu is shifted, and now mu is here, then now I have this density here and this density here, and so on and so forth. If I further move, then it will be something like that. If I move far enough, it will then resemble the regular Gaussian. I will be very far away from the threshold, and I will not suffer. Okay, so that's it. Now this complicates life a lot, because not only theta now isn't merely a shift of the distribution, it now changes completely its shape. But still, we can create a test for each one of these. test whether theta equals 1, whether it equals 1.1. We can do it by looking at the maximum likelihood test. That is, we will cut at some point here, and we'll take if the probability here is 0.95, this will be the acceptance region. I'll reject when it falls outside. I will take here. This is the idea of the maximum likelihood, that I have to take the line like that. Okay. Now, so we're going to have a test like that, but I would like to add something else to that. Notice that if we are out here and I'm cutting here, I gain very little from this extra one. Well, this acceptance region has a different sign than the original one. Maybe I can take this just a little bit here, and then I'll avoid crossing with my test in the other direction. I can gain sign determination. And in fact, this is the idea behind the quasi-conventional confidence interval. We design an acceptance region for testing theta equal theta naught, which have the correct level under the conditional distribution, when theta is the true one, but the condition is plus or minus c. The condition doesn't move, it's theta that moves. They are as short as possible, but they also include avoiding observation of the opposite sign to theta naught. And this is the idea that we've been exploring with my work with Philip for quite a while. And then we invert this to get the conditional confidence interval. And the point is that since we designed them conditionally, they control the false coverage rate, because they are each one separately, and when I average, each one of them have the right coverage. When I average them, they're fine. So we overcame the problem of selection by defining for the selected, based on the property that they were selected. Let me show you how they work. Okay, so this is an example from an ongoing study with Talma Handler, psychiatrist at Tel Aviv University. There were 16 subjects, and they viewed 2 movie segments of different stress levels. And then, using fMRI technology, MRI technology, activity at voxels in the brain was registered. And at the same time, the level of cortisol in their blood was measured. Cortisol signaling also stress in terms of hormone level. And the goal was to estimate the correlation between these differences in activity and the difference in cortisol levels across subjects. And to do that in promising voxels in order to identify on the map where are these promising voxels. Okay? So there were 14,000 such correlations, one for each voxel. And interest lies only in voxels for which the correlation is high. R is bigger than 0.6, predetermined. And there were 15 voxels with R bigger than 0.6 and 21 voxels with R less than 0.6. And this is the picture that they have. This is R bigger than 0.6. Look at the positive ones. And what I have here is the estimated correlation. So this will be linear in this. This is 0.6 and so on up to 0.69. And these are the regular confidence interval, the marginal confidence interval on the correlation. Now, they are not symmetric because we use the Fisher transformation and go back. I mean, this is a statistical I guess statistical magic, but the point is that they are correct confidence interval for the correlation coefficient, and they go from here to here. And so these are the marginal confidence interval, and these are the conditional ones. They go from here to here. You see that they extend down much more than the marginal one. They extend down, exactly doing what they're supposed to do in this direction. Going up, they extend, when the correlation is high, as much as the regular one. Notice that here they're even lower than the regular one. You don't even have to go up to the regular one, and they still offer the right coverage on the average. In fact, some of them go below the 0. I mean, the selection was of 0.6. Some of them, something less than 0 is also reasonable. It's very interesting, but in a recent study that we're making, we find out that it is better than splitting and learning, splitting the data to learning and testing. Okay, in the sense that if you, because we used to look for this 16, okay, for this bigger than 0.6, and then that we can do it by splitting the data and use half of the data to find the voxels, and then half of the data to estimate confidence interval. Then we can put regular confidence interval. It's fine because it's you didn't use the same data in order to put the confidence interval. And that's what happens is that when you use half of the data, both you discover much less because you don't use all of the data, so you discover less voxels in the brain. And the second thing is that if you use the other half, the confidence intervals are much wider because you have less data for each point. And so it turned out that this is much more sensitive, surprisingly maybe, but it's more sensitive than splitting the data and doing training and learning or estimation and validation or whatever you call it. And we have a software for that in the upcoming JASA paper. Okay. So estimation and model selection is the last thing that I want to, I guess the last thing, almost the last thing that I will discuss in detail. And the motivation is wavelet analysis, where you have a function with error, equally spaced. You estimate the wavelet coefficient, and the wavelet coefficient of your estimator is normally distributed around with the true value of the coefficient with sigma squared, which can be known, and they are independent. So the theory is fine, and that's why we started with that. And it is known that you can threshold small coefficient and reconstruct the denoised single from that. And so the idea is you transform it to the wavelets, you look at the coefficient, the estimated small ones you set to 0, you keep the big ones, and then you transform it back to the original one, and you get a denoised function. It's done with, it can be done with other bases, not necessarily with the wavelets, and so on and so forth. What is the statistical idea behind it? The idea is that if the size of the coefficient is smaller than the variance of its estimator, just forget it, zero it out. Because if you try to estimate it, you're introducing noise. So the only thing is that we don't know who is small and who is big. If an oracle gives us who is small, who is big, then we're in a better situation, and we'll compare what we do otherwise to that situation. But the point is that we can test whether mu I is 0 or not, and this is actually the hard thresholding, and the Bonferroni method is equivalent to the universal threshold of Donoghue and Johnston, which is sigma times 2 log, the square root of 2 log m, with m being the number of observation or the number of coefficient. Are people aware of this hard thresholding and so on, or is it something, I see quite a few nodding, so that's fine. Okay, from our point of view, what I'm looking at is the fact that I have many parameters mu I, I have estimators which are normally distributed about them, and I'm looking at some function of them all. And the question is, if testing is good and Bonferroni works well, what would FDR do on that? Instead of Bonferroni, use the FDR. So this really introduces us to testimation, a testimator. A testimator is something that you first test and then estimate. So the idea is you calculate PK. I know you're not interested in hypothesis testing in all. You're interested in estimation. But you first test to see if it is big or not. You look at all of them, and you find the FDR threshold, the K that you find out. So that means that you compare this one in here. That means that you threshold when your estimator is bigger than sigma times the normal quantile with exactly this point. Okay? And then you estimate by changing your estimator to 0 if you are below the threshold, and you keep it the same. If you're above the threshold, then you report it. So this testing is exactly hard thresholding. And then use this YFDR instead of Y, and this is widely used when you screen hundreds of thousands of genes, for example, and you want to model them, and your ability to model is working with thousands of variables and not with hundreds of thousands of variables. So this serves as an initial screen, and then you continue to work with what remains there. That's exactly the point. Now, interestingly, there is some theory for this situation, and quite a strong result has been derived. If we measure the performance of the estimating vector by the expected LR loss, any R between 0 and 2, that is, we both measure it in terms of the sum of square, or the sum of the absolute deviation, or something getting closer and closer simply to counting the number of errors that we make when R gets close to 0. Okay? No matter what we have. And we do it relative to the best oracle performance. The best oracle performance meaning the one who tells us who is big and who is small. And we let the number of parameters go to infinity. And we deal with bodies of sparse signals, where I will not go into the mathematical part of it, but the interesting part is you look at the proportion of non-zero coefficient, and you let them go to 0. That is, the P not M goes to 1. I mean, you're approaching the situation where most of it is our zeros, null, and very few are dead. On the other extreme, none of them is 0, but just the size of the sorted coefficient decays fast. So really fast decay. Under this condition, you have that hard thresholding by FDR testing of the coefficient with Q less than a half is adaptively minimax simultaneously over bodies of sparse signals and over all those loss functions. Meaning that counting errors, interesting, just FDR is counting the number of errors. Counting the errors relative to the things that you keep allows you to get all of this result. So what have we learned from this theory? First of all, the importance of Q less than a half, because if Q is bigger than a half, it explodes. I mean, you have to keep the FDR at level at less than a half. Doesn't matter that much, but don't get close to half. And we see it in practice that this is the case. Second thing is that FDR testing is relevant and works well even when no hypothesis is true. I mean, we started with a mechanism for hypothesis testing. We're using it where it doesn't have to be, not all of them true. Why does it work this way? Somehow, if you have small mu i's, the worst situation is when the small mu i's are at 0. So testing protects you against 0. Not because 0 is the real thing, but because 0 is the one that you protect against when the mu i's are small. The third thing that we learned is that actually the proof, a partial proof takes some 60 pages in the House of Statistics, mostly the work of Johnston and then Donovan. It's an immense piece of work, but the way the proof is done is by looking at the penalized mean sum of square, okay, where the penalty is of this form. What is this form? I'm taking z 1 over m times q, so this is the quantile of 1 over m times q, then the quantile of 2 over m times q. So those are the constants from the FDR, from the BH testing. And they are squared, and they are summed. And this is the sum of squared error. And the theory is done for that, and if you will see what does it mean, well, if I estimate something, estimate something, the prediction is it itself. So I have yi minus y is 0. So everything that I estimate, this part is 0. What I have here is all the small ones, the remaining ones. And for each one that appears here, I carry its relative zi squared over here. Now, when do I choose to estimate another one? If what I gain from this element here is bigger than the last element there, then I might as well bring it this one here and that one there. So essentially, it is very close to FDR testing if you look for the global minimum of that. And in fact, what the proof goes is that the overall minimizer is very close to the first minimizer and the last minimizer, which is using this constant in a backward or in a forward situation, or step up or step down. So both control the FDR. Now, under this setting, well, maybe we can step out of the orthogonality that exists in the wavelet analysis and before, and move in the speculative land of regression analysis and linear modeling, where the explanatory variables are correlated. So let's look at this problem. Now x, I'm looking at y equals x beta plus epsilon. Epsilon is an error, but the x are epsilon I are independent, but the x needn't be now orthogonal. So our estimator of the coefficients are not necessarily independent. Let me take beta hat S is the least square estimator for the selected model S. So I take only some of these for the purpose of model selection. As related to the model can be with all of the parameters, it can be with all of the interactions, higher order interaction, and so on and so on. A complicated model. And K will be the size of that. And what I have is y hat is the predicted, given the estimator, beta S. And the goodness of it is y minus y hat, which is the residual sum of square for the selected model S. So this is now depends on S. And we traditionally use this formulation with some lambda times the number of parameters in the model. That will cover the cases, known cases of AIC and CP and the big. They are all constant lambda. And Donoghue and Johnston's contribution is making this lambda depend on M. That is, the larger the model, the larger the coefficient that enters here per parameter has to be. So let's express it as a penalized residuals with the sum of squares as here. Okay, I'm taking the residual sum of square, adding the penalty that was served us so well in the orthogonal case. And notice that if I'm multiplying and dividing by k, I have the same type of behavior, but now the penalty per parameter depends both on the potential number of variables and on the size of the model chosen. And in fact, what it has now is that the penalty increases with the number of variables searched over, but it decreases in the model size. That is, if your data tells you that you need more and more variables, it becomes easier to include the additional variable, unlike with the constant variable. Okay, so that's the implication from this thing. Okay. So to these ideas, I would like just to add now the multiple stage procedure penalties. So instead of looking at z squared I over m, I will do it with this one, with the one I talked before, which I know that in the independent case works. And now let me use it in a forward selection manner. That is, I will use forward selection and do it in a way that will use this penalty. And I want to show you what happens from that just in examples. Okay? So I'll give two examples. The first one is diabetics data analyzed by Efron and others when they wanted to show the success of the loss algorithm. So you have 442 diabetics patients. You have 10 baseline measurements for each. And then you take all interaction except sex. Sex squared is simply sex. No, nothing helps here. So you have altogether 45 potential explanatory variables in this case. And the dependent variable is a quantitative measure of disease progress over 1 year. And all you're interested is in predictive modeling from the baseline. What will be the situation in a year's time? And I'm comparing three methods. One is the multiple stage FDR with Q equal 0.05. The other one is a method suggested by Wu, Bus, and Stefanski, which is very close in nature to the false discovery rate. What they do is they introduce random explanatory variables into their pool of explanatory variables. They run the regression until they find that the number of variables that they know is noise, the proportion in the set is less than 0.05. So they do as big as possible by introducing that. So they imitate FDR idea here. And in fact, these two gave exactly the same model, which had 17 variables. The original analysis, which used the least angle regression selection, the LARS, had 16 variables in it. This one resulted with 0.55 R square. This one was 0.53 R square. So it seems that adding, almost doubling the number of variables in the regression helped very little. And in fact, this has enough of it in order to give good results. Okay, let me go to the second example. The second example is a logistic regression, analyzing, so I'm carrying it over to logistic regression, cancer microarray data sets of normal and carcinogenous lung tissues. Microarray analysis, number of probe set is about 7,000, number of cancer samples and the number of normal samples. It has been analyzed a couple of times. Beer et al. Is the original one. It was analyzed and published by a group of researchers at our universities. I'll save the names. The goal was to produce a stable ranked gene list, the top of which would be a good set of classifiers. Okay, so what they did is the following. They produced 1,000 different gene sets according to the SVM models of sizes 5 up to 100 on bootstrap samples. That's the addition. Yesterday I didn't know. Okay. So what they did is they bootstrapped the samples, keeping the 10 and 86, and reran again SVM model selection. First of all, limiting to 5, then to 10, then to 20, then to 40, all the way up to, actually they did from 5 on, 10, 15, and so on, all the way up to 100. And registered what variables entered the SVM models. And then they looked at the highest rank, those that appeared in most frequently in those sets. And the gene with the highest score was a gene with RAGE, it was called. And this is the way it distinguished between the two tissues. So these are normal samples, and this is counter samples, and these are the box plots of the gene expression level for the two of these. Not great, I would say, the least. Okay. Now, what we did is we used the multi-stage FDR penalty. We also produced 120 replication by bootstrapping. And for each replication, we got a sequence of nested model by forward selection. That is, we added the one variable, then the next one, then the next one, and so on and so forth. We fit logistic regression for each of the subsets on this sequence. And we chose the minimizer of the deviance, which is instead of the sum of squares, it is -2 the likelihood, plus the multiple stage FDR penalty. Okay, and we did it 120 times. And the result was that in all replication, only one gene was needed. No more than one gene. And here is the box plot of the separation by the top genes in this case. So for the 6 top ones by themselves, this one perfectly distinguished between the normal and the cancer. And so is this one, and this one except to one. All the others except for one patient distinguish entirely. Now, what happens there? How can this extensive thing miss and this simple forward selection, but controlling for the fact that you select a few from many, why does it give you such a thing, such a good thing? Well, the point is that the possibility of selection offered is so big that noise overwhelms, the noise created by the selection completely overwhelms the true underlying small feature. So this is an example where the fact that you don't have power is better than you will have power, but it will save you the day. The question of model selection is just model selection. You select a subset of the variable. So far, we've talked about model selection in prediction. But the last example actually shows that even if you do prediction, you're interested in what you found. I mean, the interest here is not merely to get a good prediction, but to understand by what was it predicted. That explanatory thing is of if of answers. And so the question is, what interpretation can we give to the parameters in the model selected with FDR penalty? Hopefully, we would like to have some property like we are protecting the false dimension rate. That is, the dimension we include in the model, maybe not exactly the parameters, we don't have a zero interpretation for the parameter, but we don't have too large a proportion of that. It is not clear. Our current theory doesn't give us a help of that, because remember, as we move on, the parameters change, the estimator change, the p-value, something that was a big p-value before, once a new variable enters, the p-value may deteriorate or may get better. My hunch is that it is indeed controlled, maybe with some small adjustment, but it's, I don't know. The second question is this forward selection path that I was using, is it essential? What about the lasso, the last path, or subset? I mean, other things that one can use for model selection, but you still want to infer about what exists in your model and makes a statement, and about the size of it, and make confidence interval, and so on. Now, this is really at the core of current work, I think, in the area. Actually, 3 current papers out of Stanford teams deal with testing along the lasso path while controlling the size of the model using FDR idea. They're all from the last half year, essentially. The first one of these is the idea of data splitting. Well, you develop the model on half of your data, and you estimate the significance and confidence interval on the other half of the data. The other one is asymptotic p-values for the lasso path when you introduce new variable into the lasso path. A third one is a sequential testing idea that might be looked at there. And the fourth one is this paper by Candes and co-author, introduces sorted L1 version of FDR penalty, which is neat because what it does is that we looked at this penalty, okay, least square plus this, and in the spirit of the loss, you're taking not merely the absolute values of each of the coefficient, but you multiply it by a penalty depending on the order it is. So the largest one, you give a large penalty. The smaller you get, the smaller the penalty. And you minimize that, and so you can use ideas from least squares, and you can avoid using least squares and the computational complexities, and instead use other things. These are 2 new. I'm just pointing at the fact that there is a lot that is going on in this direction. It is something that we are working on part of it, with Philip more on the confidence interval part of it after model selection. But it doesn't have yet a good answer. So you asked me in the beginning, we don't have yet a good answer, but I think we have, in terms of the selection part, we do have. Okay. No, that's what I said before. I just want to mention that part of the interest is because of the recent result of Berg, Brown, and Bourget that solved the problem entirely, but solved it in the family-wise error rate control over all possible selected models. I mean, they solved a huge problem. By solving the huge problems, they protect against any model selection, at the expense of extremely long confidence interval that go like the square root of m. M is the number of potential coefficients. So in fact, it's just making the statement this is an open problem. How to utilize the selection process in order to get reasonable inferences. Okay. I have about 15 minutes, as I said. Okay, I will start with that and then stop in the middle and move to another issue. Yeah.
Can I ask a question before? So, if I understood correctly, the underlying modeling here is that you've got this quickly decaying list of sort of good, true, like in the case of independence, you were assuming that the means were quickly decaying, and you were looking for those
sparse signals.
Yeah, sparse enough. You're looking for that heavy part. I guess a different approach would be to not assume anything about the sequence and just hope to get something like the best, like a small set of good variables, or just to be competitive with the best small set as opposed to recovering everything. And I guess I was just wondering if these analyses sort of are general enough to encompass that kind of setting also.
Okay, the kind of theoretical analysis that was done for included many types of sparse bodies, but sparse. So they can be L2 balls, I mean the Sobolev balls, I mean all kind of this theoretical stuff, but in particular if they're all non-zero, they go down fast enough to zero, and so on and so forth. In terms of theoretical analysis, I don't find it very useful to study specific things. In specific things, I would do it in terms of finite problem size. And in finite problem size, I will bring here, we did some extensive simulation studies, assuming all kinds of dependencies and so on, and got sort of the least favorable situation, protection against the least favorable situation was very good by this method. Was actually the best, and had one more thing, which is asymptotically similar to that. I didn't saw it. It is hard for me to see how you can. We have very limited results under the non-orthogonal situation, so I don't see the point of getting finer results in the orthogonal case, while really we almost always face the non-orthogonal case. So if an effort is to be done, it should be done in maybe even smaller problems, but ones that are realistically in the situation. So far, it's mostly done with simulation and not with, but it's a challenge. It's certainly a challenge.
So we'll need to finish about at noon, because we'll have another presentation after yours. We have about 7 more minutes. Can you?
7 more minutes. Okay. So I will just finish with 2 things. First of all, I was talking about a family, and in fact, this last part I wanted to talk about families of families in a very diverse way. And what I wanted to emphasize that while there seems to be ambiguity about the notion of a family, for me it is defined by the possibility of selection. So a family is the richest set of inferences in an analysis, all achieving the same goal, from which one selected inference could be replaced by another selected inference for presentation, for highlighting, or for action. So it is different researchers can have different goals and thus define differently the families, but still decisions can be defendable and with no arbitrariness. Okay, and an example is medical research, where you have usually or clinical trial, where you have a control group and a treatment group. And you first do a baseline comparison, and there's a lot of p-values about baseline comparisons. Then you have effectiveness of the results, and you might have 6 or 7 measures of the effectiveness of the results. One of them will be called primary endpoints, the other one will not, but those describe the efficacy of the drug. And then you will have another table describing the safety. Now, one cannot take something from safety and bring it to the baseline or to the efficacy. Each one has a goal by itself. And so the goal is defining, the goal and the ability of one replacing the other in order to make a statement is what defines a family. And I will immediately go to the ones I presented here, that really the researcher didn't do the analysis this way, but the way they presented the results, they defined their own families. Because what they did, and this is a family of families, what they did is they first selected the 5 top genes. They weren't significant, but they selected 5 top genes. So that means that they looked at the genes as a big family, and they selected only 5. Then for each SNP, they selected the family of interesting findings. From where? From different regions on the brain. So they looked at all of these as one family and made their selection. And it didn't matter if it was here or there. So the researchers reveal, in fact, what is for them a family or not. You can argue with that, or you can agree with them. But it's not something arbitrary. That's the point I'm trying to make. And with this note, I will go to the last point that I wanted to make. And this is selective inference challenges in open access data, which might be of particular interest to that. Well, we are now having more and more cases of open data. And that's really what you're dealing with in a way. I mean, you're dealing with the problem of confidentiality in open data. We have the same problem with selective inference when open data. For instance, the European community have decided that as of January 1st of 2014, all clinical trials results should be deposited in an open access database on individual patient level, and should be available for other people to study, to reanalyze, to look for different results, and so on and so forth. So the question is immediate, that of selective inference. Suppose that you will have this 100 different people going to the same database and asking again and again. At the end, something will come out. So it's interesting to know that actually FDR ideas can be adapted to that, while family-wise array completely cannot. Because it's the family-wise array, the family, you have to know from the beginning the size of the family. And it so seems that I, too, so far have discussed only issues where the size of the family is given beforehand. But that doesn't have to be the case. In fact, over the break, right, I talked with Nimrod Megiddo, and I presented this tree of hypotheses, and in fact say that we can have control over a tree of hypotheses that will give us control whatever the tree is. Whatever the tree is, which means we don't have to know it beforehand. But the only point is that we do not continue with something, or 2 points. We do not continue with something unless it was significant. And at each level of the tree, we do FDR testing at level Q. And the thing is, it doesn't more than doubles the FDR, double times 1.44 or something like that, which is the upper bound. Another idea is that by Forster and Stein, they talk about alpha investment to control the level alpha Q. They're talking about hypotheses coming at a row. Okay? And you control actually, if it was, if I were F1, I would put here a little big FDR and here a little FDR, because they're talking about E of V divided by E of R, and just add a little bit of mu to the numerator to take it away from 0. It's not that essential. And the hypothesis arrive sequentially in the study, and you test HI with alpha I defined beforehand, but that can be modified. That is, if you've rejected I, then alpha I plus 1, the next one, will be larger. Why? Because if you've rejected, you've increased your denominator. While if you've not rejected, you might have been adding to the expected value V. So the thing is being modified, and it's a very nice idea. They weren't thinking at that time about open access data, but it is really appropriate to think about it in a way. And in fact, Aroni and Rosette just recently suggested an optimal rule for that, and in fact combined it with quality-preserving database idea that if you go and analyze the database, you have to contribute some new cases. And they showed that if you do that, you don't have to contribute much cases. And actually, while everyone seems to be using more and more, smaller and smaller alpha to decide that a rejection has occurred, in fact, the power remains stable. So the fact that cases are added, you keep a stable power at the same time. So the point I'm making is I think these ideas they are ripe for further utilization and can be used to address issues in open access data. Okay, so let me finish by reflecting on the outline. I talked about simultaneous and selective inference, making the distinction, talking about the family. I hardly talked about when should we use simultaneous or selective, nor did I talk about the many other error rates that are being explored sort of in between, like the probability that false discovery proportion will not be less than 0.05 will be bigger than 0.95. And things somewhat more complicated on that level. I didn't talk about that. Testing with FDR control, I talked about the BH, the adaptive BH. I didn't talk at all about resampling, which is heavily used in genetics where you have the original observation. And I mentioned just the empirical Bayes. In the false coverage rate, I did talk both generally and tailored to the selection. I didn't talk about complex selection or about the issue of dependency, which creates a problem. And in the estimation and model selection, I talked about FDR thresholding, its equivalence in terms of penalized MNC. It showed some example. I didn't talk about conditional estimators and just mentioned the fact that we have a problem with post-model selection inference. And I didn't talk at all about more complex family. So let me sum up that I hope that you will carry over from this talk is that you have to worry about the effect of selection. If you get out from here with this resisting in mind, I've done a good job. It might be enough to show properties on the average of the selected, which is what the FDR approach is doing. And there are simple and useful methods for testing confidence interval. And the ideas seem to be important in other situations for analysis of big data and large inference problems like model selection and open data access. And there are many challenges that still exist in the area. And I'm sure that more challenges will come as the scientific questions become to, or the practical questions come to mind. Thank you.
Okay, we still have time for some questions if there are any.
Yeah. Oh, sorry.
Back in the back. Go ahead.
So you selected examples to show us here the success of the FDR.
You forgot my request, my initial request.
You actually selected few good examples to demonstrate FDR out of how many thousands of examples are in the...
Okay. Good question, especially since I have an answer. So there is a recent paper in biostatistics where Lick and his wife, Jagera, I think, actually tried to answer the question by mining all the abstracts of 5 leading medical journals, the Journal of Medicine and British Journal of Medicine and so on, the 4 leading journals, and the 5th one was an epidemiology journal. Mining all of the p-value statements in them and trying to estimate from that the false science-wise discovery rate. So science-wise false discovery rate. So actually looking at the phenomena. And they published this result. They came out with a very low figure of 0.15. We not only discussed this paper, but used the software which was reproducible research, and we could easily do that. And together with Yotam Heflinger, we actually tried to look at it again, actually sampling papers, they mined abstract, looking at what is the relationship between what appears in the paper and what in the abstract, and so on and so forth. What I can say is that I was very merciful in my examples. Okay, we estimate it to be much closer to somewhere between 25 and 40%. And this is because of the phenomenon of selection into the abstract. I mean, you see in the paper, everything is scattered with, significant p-values and not significant values, but then in the abstract, it's only the significant that appears, and so on. So it's, I don't think we fell into this trap.
Any other?
So you mentioned at the very end this sort of interesting problem when hypotheses are being chosen adaptively, like the hypothesis is chosen only after seeing the results of hypotheses 1 through.
What, the 10 leading ones?
Right. Does this approach need to, and you mentioned there was some approach for handling this, does it need to know what the sort of tree is for choosing the hypotheses? Or is there anything you can do so that you didn't know?
What, for the tree structure thing?
Yeah.
You can develop the tree while you're doing testing.
But what if the tests are being done by different research groups?
That's great, because you need independence. So that's a good thing about it. So in science, what I envision, hopefully will happen, is that, a scientist continues to work on something that seems to be promising. So in this case, a scientist here has decided to create a study because this was a significant finding that appears in the paper and so on, and he continues with that. Now he's continuing it by himself, okay? And if he makes a finding, someone else will continue and so on. But the practice of meta-analysis, where you collect all studies made by independent researchers, look at them in a combined way, this is essentially doing this step or doing this step. So it is true that the tree is, in some sense, going faster in this direction than back, but that's the point. When I talk about it, I'm trying to emphasize the importance of meta-analysis to keep honest that, in fact, there was an example of, I think, tamophilin. I mean, the drug against the virus that was brought to the market in huge quantities for the birds flu. Okay, so there was an analysis of that, and there was about I think 12 different studies, but essentially only one of them was a very strong results. And when you looked at all 12 together, and looked from this point of view, not from combining everything together, because meta-analysis sometimes simply combines the thing, but you looked at the question, is there enough evidence? You would say no, there's not enough evidence. So it's true that it was done after the case, but it can protect the scientific progress in a very nice way.